Hi everyone, I have more than 15 years of experience in design verification. My name is Suri Babu Talla. Let's talk about the AI driven verification in the new era, such as intelligent validation strategies for next generation VLSI systems. Before going to the AI driven verification, I want to touch about the traditional verification methods in VLSI. The first one is IP based verification. Validate each IP block in isolation before integration using the constrained random verification directed tests and assertions. And next one is the SoC level verification. Those which are verified in the IP level blocks will integrate it at the SoC level, and again we are using a directed test cases, and sometimes we'll use hardware software co-verification for the verification. The third method is like a platform level verification, which we will integrate all the blocks along with the full system. We validate full system along with the firmware and OS by using the firmware plus driver bring up validation complete platform as it behaves in the real-time hardware conditions. The changing landscape of VLSI verification. Transistor density. As design grows from previous generations, now transistor density reach until the multi-billion transistor threshold, demanding verification at unpredicted scale. Heterogeneous systems. As design increases, we have lots of complex modules which has CPU, GPU, AI accelerators and custom silicon blocks which will integrated into single SoC, which will cause the multiplying interaction complexity between the two modules that has to be addressed during the verification challenge. Verification pressure. This is requirement from the verification schedules are tightening even as design surfaces are expanding dramatically as compared to the previous generations. Challenges in traditional verification. Conventional verification methods were built for a simpler era, a design complete scales. Those approaches are shown critical strain at every stage of the flow, such as cycle length. Long resource intensive runs consume weeks of compute time per tape out, which will consume lots of human resources and timelines. Scalability gap. Coverage closures becomes exponentially harder as the design size and features count grows. And the issue is the corner cases. Rare high impact bugs remain exclusive under the random or directed text strategies. To avoid these conditions, we need an intelligent systems. The next slide shows how the intelligent systems will work. The need for intelligent systems is traditional rule-based verification cannot keep pace. AI introduced data-driven decision making that lens adopts scales with the design complexity, which is missing during the traditional verification. Learn from the past. The AI models trained historical simulation identity patterns invisible to human engineers. Generally, human engineers are not taking as a historical simulation data for the reference. AI models will take that and make its own training. Automated runtime. Repetitive tasks and regression logs parsing coverage analysis become automated and instant. For every database change, the automated tools are automatically initiated and it's parsing the logs and coverage analysis and become automated at that instant and give all the graphs required for human interaction. Decide at a scale. Machine-driven prioritized directed compute resources to the high-risk design regions first. Unless in the traditional verification, the AI-driven verifications are like targeting for the high-risk regions first because it knows that like from the previous projects. Continuous improvement. Self-improving systems grow smarter with every verification run, computing gains over time. Because AI uses the machine learning concept and it will remember it previous failures and every run it will improve it like decision making. Yeah. that will impact the overall verification shift in the new verification AI era. AI paradigm shift in the verification. AI and machine learning integration is not an incremental improvement. It's a fundamental rethinking of how verification flows are architected, executed, and optimized. There are certain flows they call adaptive flows, verification environment that reconfigure themselves based on the design feedback and coverage. Called reduced intervention, manual response streams dynamically as AI handles stimulus generation, drainage, and reporting. Smarter cycle, validation turnout compress from the weeks to days with intelligent scheduling and then resource allocation. How the technologies is useful to powering this shift. The first is a predictive analysis, a prioritized test, which generally in traditional verification we will use the regular flows, and predictive analysis, it will prioritize the test and anticipate the risk of that test, and then we'll execute those tests at first level. Supervised and machine learning, learn from labeled verification data. It will take a data from previous projects and label into a verification learning mechanism, and will improve the machine learning. Reinforcement learning, optimize the test strategies through the trial and feedback. It will have the trial and then read the results, and again it will rerun it again to optimize the learning. Anomaly decision identifies rare and unusual simulation patterns. Each technique addresses a distinct challenge in AI verification pipeline. Together they form complementary AI stack that spans planning, execution, and debug, delivering coverage against single method achieves alone. The four pillars are increasingly supported natively within commercial EDA platforms, lowering the barrier to adoption. Next, we will discuss how the predictive analysis will work. The predictive analysis, rather than treating all design blocks equally, predictive models score risk across the design hierarchy, directing verification efforts where it matters. First, it identifies the risk identification, flags high complexity modules and untested corner cases before simulation begins. The next one is text prioritization, ranks scenarios by predicting a bug likelihood to front-loading highest value test. Resource optimization, allocate the complete budget, dynamically reduce the wasted cycle and low risk regions. Yeah, the next topic is like how we can generate the intelligent stimulation, and how we can target like a coverage goals. AI-powered test generation moves beyond a random and directed test approaches, producing a targeted stimulus that exercises precisely the scenarios is most likely to expose hidden bugs. Coverage analysis. AI identifies the uncovered functional space from the prior runs. Targeted generation. Constrained random sequences are guided by learned bug strategies. Adapt to test bench. Test bench parameters self-adjusting in a real time to close stubborn coverage holes. Bug escape reduction. Faster direction of deep, rare defects where few total simulation cycles. Anomaly detection. Statistics models trained on a baseline simulation behaves can flag deviation that signals are latent bugs, issues that would otherwise surface only during the silicon bring up or wars in the field. Pattern deviation detects statistical usual simulation outputs against the land baseline. Rare bug exposure surfaces the latent defects that random or directed tests routinely misses. Verification confidence reduces the post-silicon surprises by raising the bar on simulation fidelity. AI cross verification workloads. Generally, we use like several workloads: a statical verification and dynamic simulation testing, hybrid coverage status, continuous feedback loops. They enhance both static and dynamic verification, creating a unified continuous coverage strategy. The first is static formal verification. AI-guided property decomposition and constraint synthesis reduce the state space exploration in a formal tools, enabling a broader proof coverage. Dynamic simulation, intelligent regression selection, and adaptive simulation generation cut the simulation work clock time while improving functional coverage closer. Hybrid coverage statistics. Combining formal and simulation results throughout the ML models identify the residual coverage gaps that neither approach catch alone. Continuous feedback loops. Each computer each completed run feeds the data back into the AI model, incrementally improving predictions across the future verification cycles. Next we'll discuss how AI in formal verification. AI in a formal verification offers mathematical completeness but struggles with the state space explanations. AI transfers formal tools from the specified instructions into a scalable prediction grade engines. Intelligent constraint solving. Machine learning guided solvers navigate large constraint spaces for more efficient than extensive search. Faster proof coverage. Learn fewer irrelevant proof branches, reducing the verification runtime significantly. Enhanced property checking. AI suggests auxiliary invariants that strengthen property proofs and improve completeness. Next, we will discuss the accelerated root cause analysis. In verification environment, we have like a several debugging techniques. We'll open the waveforms and we'll review the logs, those kind of things. How can we can accelerate by using AI tool. Accelerating root cause analysis. Debug is historically the longest phase of verification. AI compresses the dynamically by automating the most time-consuming analytic task. That is large long waveforms, cluster and classify divided into several clusters design, predict and rank causes, and it will predict and give the certain ranks to the design component. Engineer, review and fix. Those all details will give you the engineers and he will review it and fix settings. By cluster failures and predicting root cause analysis before an engineer opens the waveform, AI-driven debug can reduce the mean time to root cause by 50% more than complex exploitative faults. Practical impact. Next we'll discuss the practical impact of real world results. Practical impact of real world cycle reduction, verification runtime savings reported in AI accepted flows at a leading semiconductor firms, coverage velocity, faster functional coverage closer compared to traditional directing random strategies, redundancy eliminated, reduction in redundant simulation scenarios throughout the intelligent test duplication, debug speed, faster root cause identification enabled by automated waveform and log analysis. Trust, transparency, and responsibility. As AI seems to be got greater decision-making authority in verification flows, the industry must address critical questions of reliability, explainability, accountability. Explainability. Models must provide human-readable justification for coverage decisions and failure classifications. Training databases. Model trained on a narrow design may fail on a novel architectures. Diversity in training sets is essential. Decision reliability. AI recommendation must be validated against a non-grounded truth before being used. Gates and human wants it. Engineers remain accountable. AI amplifies the judgment, it does not replace it. The road ahead. AI navigator frameworks. Verification platform build AI first, not AI augmented with intelligence embedded throughout the flow. Self-learning systems, adaptive units that continuously refine models across the design generation without manual retraining. Deep EDA integration. AI verification intelligence embedded actively in commercial EDA tool chains for seamless adoption. Resilient chip design. More robust, higher confidence silicon outcomes deliver faster, lower verification cost. Key takeaway: AI is transferring verification from a manual, reactive process into an intelligent, proactive system, making it most consequential shift in VLSI validation methodology in the generations. Question is AI can how can AI-driven techniques improve verification coverage and reduce simulation redundancy in a complex AI systems? What are the key challenges adapting in AI existing verification workflows? How can they address? How AI-driven techniques improve the coverage and reduce the simulation redundancy? Let's explain that. AI improves both depth and efficiency of verification by making every simulation cycle more intentional instead of random. First, AI risk-based targeting instead of uniform effort predictive analysis. Predictive models score risk across the design hierarchy and directing a verification effort where it matters most. Smarter coverage-driven simulation, similar generation. AI-powered test generation moves beyond the random and directed approaches, protecting targeted simulations that exercise precisely the scenarios most likely to expose the hidden bugs. Hybrid covers from formal plus simulation. Machine learning models fuse formal and simulation results to reveal residual coverage holes that either alone can see or improving the coverage rather than just adding more tests. Combining a formal and simulation results to the ML models identify the residual coverage gaps that neither approaches catches alone. Redundancy elimination via intelligent selection. AI A prompts low value or duplicate regression by learning which tests rarely find the new bugs, cutting time without sacrificing the quality. Reduction in redundant simulation snaps through the intelligent test duplication. Detection for rare bugs. Models trained on a baseline simulation behavior can flag deviations that signals the rare or latest bugs. Net effect: higher functional and formal coverage with fewer or more targeting stimulus. Next question. Key challenges in adopting AI verification workflows. How to address them? Technical promises only works if the trust, transparency, and process integrations are handled carefully. The first challenge: explainability of decisions. AI and sign-off decisions require auditable reasoning. Black box models are insufficient for safety critical chip designs. Second, training databases and generation. Model trained on narrow set of past designs may fail in a new architecture nodes and workloads. How to address them? Diverse training across IP types, process nodes, and verification styles, continually trained with the feedback from the new projects. The next challenge is decision reliability for the sign-up. AI recommendations must be validated against known ground truth before being used to gate off and sign off. How to address them? Start with AI as a recommendation layer, not an authority. Compare its choices against the historical bug data. Define guidelines, minimum traditional coverage thresholds, mandatory human reviews for safety critical paths. The next challenge is human trust and role clarity. Engineers remain accountable. AI amplified judgment does not replace it. Thank you.